Let's construct truth tables for these two well-formed formulas. A or B negated, so not A or B, and also not A and not B. So that's a WFF, that's a WFF, right? There's our four combinations of true-false values for these. So if I look at the first one first, I'm going to produce A or B. So we know only one of these needs to be true for the entire expression to be true. So it means we have true, 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 and false, because false or false has to be false. And now if I negate this, remember we did the parentheses first and the negation, then it becomes false, 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 and true. Right? And this is what we're producing here. Now let's produce this. I need to do these individually. So not A, not B. So this would be false, false, true, true. And this would be false, true, false, true. And now when I AND those, not A and not B, this would be false, 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 and true. So that's this. So what was the point of that? Well, let's look at these two. For this combination of A and B, this produced false, and this also produced false. For true and false, I got false and false. For false, true, I got false and false. And for false, false, I got true and true. So what that means is that these two expressions are equivalent. WFFs, right? And we would normally write this like this. We would put this here, bar, bar, bar. So it's like a triple equal sign. Now note some authors will use this symbol, this sort of two-lined double-headed arrow, but then some other authors use this for something else. I prefer this, which I didn't invent. Some people also use this, but I think it's much more clear. Okay? So what's the point of this? Why do we even care? The reason why we care is because this says that everywhere we see this expression, we can replace it with this expression. Okay? So what if I had, say, just a regular algebraic expression? If I had, 2 times 3 plus 5 minus 4 times 3 plus 5. Well, I know that 3 plus 5 is 8, so I can put 8 there and also just put 8 there. And I still get the same answer, right? 3 plus 5 is equal to 8. They're interchangeable. I can replace each 8 with 3 plus 5 inside parentheses, right? Or go the other way. These are the same way. And so the benefit of knowing about these equivalences is that when we start to see larger expressions, we want to manipulate them just like we would algebraic expressions. We want to manipulate them to where we can eventually get some answer. Okay? And often in textbook problems, you're given an answer. Said, okay, show that this is equal to something like this. And so we manipulate it. Maybe I see this, and I replace it to this because this may make it easier than to do something else. Okay? So there's a number of these. So let's look at some of the basic ones. And some of these will be somewhat obvious. Right? So these are equivalences. So let's write this. This should make sense to you. A or B is equivalent to B or A. This is just logical or. So it should make sense that which one's on the left and which one's on the right is really irrelevant, right? And likewise for and, it doesn't matter which one's on the left and which one's on the right. But these are examples of the commutative property. Just like for real numbers, we know that 3 plus 5 is equal to 5 plus 3, right? It doesn't matter which one you put on the left, which one you put on the right. We also have associativity, right? 2 plus 3 plus 5 is equal to 5. Or in that case, for associativity, it would be 2 plus 3 plus 5 is equal to 2 plus 3 plus 5. Well, same type of thing applies here. So we could have A or B or C is equivalent to A or B or C. And we have A and B and C is equal to, sorry, no parentheses there, A and B and C. This is associativity or the associative property. Right, we have a distributive property. A or B and C is equal to A or B and A or C. And we also could have A and B or C is equivalent to A and B or A and C. And we'll put parentheses to make sure that's really clear. This is the distributive property. Okay? The ones I showed you a moment ago, or that was one of them, is what's called De Morgan's laws. So we have these. There's two of them, really. Notice on these, if I have or inside here, then when I push the negation inside, it becomes an and when there's an and here, it becomes an or over here. Okay? And also pay attention on this. The way I remember the distributive ones is I think of like multiplication and addition. If I had A times B plus C, then it becomes A times B plus A times C, right? The same symbol here is the one that goes here, even whether it's and or. Okay? We've already seen this. A or true is just whatever A is. Or actually, we didn't quite see it, but that's the case. Or excuse me, this is false. And A and true will just be A, okay, because the true here is always going to make it, if we have like true and true, well, A was true, and so we get true. If A was false, then the whole thing becomes false, which is really what A is. The ones what I started to say, the ones we actually saw were these. A or not A was true. A and not A is always equal to false. There's some others beyond these, and these are called identity and complement. There are others besides these, and we'll see some more, but these are the basic ones. And like I said in the beginning, the whole reason why we care about these is that as we get larger expressions, in order to reduce it to something we can understand or to show a certain thing, there's lots of times we need to say, okay, you take this and turn it into this, or you take this and turn it into this, or whatever, especially like De Morgan's laws. It's very common to see the left side and you turn it in the right side in order to get, not A or not B, or something like that.